Hello, physics students. Let's talk a little bit about graphs. I'm going to put 3 graphs up here on the screen. I want you to go ahead and draw these in your notes. Each of these graphs describes the motion of an object. Pause the video and just write a quick description of what's happening to the object's motion. Okay, so depending on your background, you may have written some different things here. So maybe some of you wrote speeding up, slowing down, and constant speed. Okay. Now, some of you may say, wait a second, that's not right, because when I think of speeding up, slowing down, and constant speed, I'm thinking of graphs that look like this. Speeding up, slowing down, constant speed. And these graphs look a whole lot different from the ones in the top row, because people in the bottom row are saying the ones in the top row really are showing a constant positive velocity, a constant negative velocity, and a velocity of 0. Well, it turns out no matter which you wrote here, or if you wrote anything else, you're actually wrong, because without any context, you can't tell at all what's happening. The axes are not labeled. And so let's really delve into what we do know about graphs and how we can analyze them. And we're going to start with some general statements. We'll start with this. The slope and shape of a graph have meaning. This is why we plot graphs, because they reveal information that we can't tell just by looking at patterns of numbers. And once you figure out what the slope represents, then you can look at the shape of the graph, and that will tell you what's happening to the slope and what's happening to that physical quantity represented by that slope. We move on to say the slope of any straight line has a constant value. In fact, the mathematical definition of a straight line is a curve with constant slope. So when we put these two ideas together, once you figure out what the slope represents, if the line is straight and has a constant slope, that's telling you that physical quantity remains constant. However, if the slope is changing, that's telling you that physical quantity is changing. So if we go back to these graphs here, what can we write about the top graphs? Well, they're all straight lines, right? So the first one would be a constant positive slope, and so it's linear with a positive slope. It's a straight line, the slope is constant and it's positive. Second one is also a straight line, so the slope is constant, but it's negative, so constant negative slope. And that last one, well, it's a straight line, so it's a constant slope, but specifically it's a horizontal line, so the slope is 0. And then once you figure out what the slope represents, that will tell you that there's a constant positive whatever, a constant negative whatever, or that quantity is 0. What about these bottom ones? What's happening here? Well, clearly the slope is changing with these ones, right? The first two, I should say. So this one has a slope that's increasing. This one has a slope that's decreasing. And since this is the exact same graph as that one, there's a constant positive slope. So once you figure out, based on what is being plotted, what the slope represents, that would tell you this quantity, that slope is increasing. This has a quantity that's decreasing. And this, again, is a constant quantity, just with a positive value. Let's continue talking more about graphs. There's a critical, important idea here, that graphs are linked to equations, and that's going to help you understand what you're seeing in the graph, what the slope represents, and what other things could possibly represent. One other thing I might calculate from the graph is the area. Here I put often because this is used a little bit less frequently as the slope, but certainly it could be used to get some important quantities. Now, when we talk about area on a graph, what we really mean is the area between the line on the graph and the horizontal axis. Sometimes it's called area under the graph, but that's a bit of a misnomer. Let's talk about the kinematics graphs, and here's a little bit of a graphic organizer about graphs that's going to help us organize our thinking. These are the graphs you're probably most familiar with from previous experiences in physics: position versus time, velocity versus time, and acceleration versus time. And if I were to ask you how to get from position versus time to velocity, you say, well, I'm going to be calculating slope. I'm sure you'll all remember that. And if you have a velocity versus time graph, what would you do to calculate acceleration? Again, you'll probably remember that it's going to be calculating slope. Well, how do we know that? Well, it's about this idea that graphs are linked to equations, right? Whenever you find the slope of any graph, it's always rise over run, or delta y over delta x, but then you just line that up to what's actually being plotted. So on position versus time, that's delta x over t, vertical over horizontal, and that, of course, is the equation for average velocity. On a velocity versus time graph, delta y over delta x is delta v over t, and that lines up with the equation for acceleration. So here's how we know what the slope represents. And it's not magic. This is how you figure out the slope for any graph. Just take the delta y over the delta x, line that up to some equation you already know, or maybe look at the units if you're not quite sure about it, and that most likely will be telling you what the slope represents, what physical quantity it represents. We can also link this to the idea of writing the equation in a y equals mx plus b sort of format. So if I rearrange this as delta x equals v bar t, if x is plotted on the y and t is plotted on the x, this says y equals mx plus b, and v bar is playing the role of slope. If I do the same thing here, delta v equals at, where velocity is plotted on the y and time is plotted on the x, well, this says y equals mx plus b, where the acceleration is playing the role of the slope. So this is what I mean by the graphs are linked to equations. Let's talk about area. Hopefully you remember that if you had a velocity versus time graph and you want to find information about position, you're going to be finding area. In reality, though, you're not finding position, you're finding change in position, you're finding displacement. From a graphical perspective, this is the velocity versus time graph. And if it were a constant velocity, and this dashed line here sort of bounds a shape here, you can see that this is sort of a rectangular shape, and this is the length, this is the width, and so finding the area of this rectangle is literally doing this, delta x equals v bar t. And so you can see that x times y, or horizontal times vertical, gives us displacement. So again, the graphs are linked to equations. Here, the equation is telling us when we find the product of the two quantities, we're finding the area. If instead you had an acceleration versus time graph, and we want to find information about velocity, well, now again, it's going to be area where once again, it's not velocity, it's actually delta v. And here again is an acceleration versus time graph. Same general idea. We have this rectangular shape. Length by width would give us the area, which is a times t. And again, the equation shows us a times t gives us delta v. So again, we could always be thinking about what equation is linked to that graph. And then if you're dividing things, that will tell you some information about slope. If you're multiplying things, it'll tell you some information about area. You can use these techniques for really any equation, any graphs, and any equations, and not just about the kinematics graphs, but these are the ones we're most familiar with. Let's take a look at a velocity versus time graph and talk about the area, specifically that we're talking about the area between the graph and the horizontal axis. So what's happening in this motion? Well, the object, maybe it's a person, starts at a speed of 2.5 meters per second and then slows down to a speed of 0 in 1 second. And then now we have negative velocity, so the person must be going the other direction, and the magnitude of that velocity is increasing, getting larger and larger. So the person is slowing down in the first second, changing direction, then speeding up in the other direction. Let's find some information about displacement, which would be given by the area. So when we talk about the area between the line and the horizontal axis, here's the line and here's the horizontal axis. So there would be this triangular area there. And since we're dealing with positive velocities, this would represent a positive area, which I know sounds a little bit weird, but if you think about it, the person started moving, let's say, forward at positive 2.5 meters per second, and then slows down to 1 meter per second. So the person's still going forwards with a positive displacement, and this is represented here by a positive area. At the 1 second mark, the person stopped moving, and now it's going the opposite direction. So the area we're looking at is here, and this involves negative velocities. The person's going the other way. This is represented by what we call a negative area, because now the displacement is negative, right? So the person was going forwards in the first second, and then backwards in the next second. And so when we talk about area, again, we're talking about the area between the line on the graph and the horizontal axis, not the area specifically under the line. Here we're going to link the graph to the equation Vf equals v naught plus at, and when I write it in this form, which I'm sure you're familiar with by rearranging the acceleration equation, this literally lines up to y equals mx plus b, where we're plotting velocity on the y-axis, time on the x-axis. We know the slope should represent acceleration, and certainly it's playing the role of slope. And here, the initial velocity is the y-intercept, which makes perfect sense. That's the starting velocity when time equals 0. So you can see, again, we link graphs to equations because it helps line everything up. Let's look at another equation here. There's the time-independent kinematics equation, Vf squared equals v naught squared plus 2a delta x. What shape should we expect from this graph? Well, right now it's not really set up to plot what we want. We really want to plot the speed versus position. So I'm going to take the square root of both sides. Vf equals the square root of everything on the right. And just to make things a little bit easier, let's assume the object starts from rest. That's not going to be every case, but it'll make it a simpler situation. So if the initial speed is 0, that drops out. And now we have Vf equals the square root of 2a delta x. So is this a linear function? Well, no. Linear functions have a degree of 1. And if we're plotting this against position, the position is not raised to the first power. Since it's under the radical, it's raised to the 1/2 power. So it's not going to be a linear function. What shape will it be? Well, it's going to be this. This is what's called a root curve, because the speed goes as the square root of position. Alternatively, you could think of it as a parabola opening to the right. But I like to call it a root curve because that reminds us there's a square root in the equation, and we're trying to link graphs to equations. Now, from this graph right now, without calculus, we can't get any information from it. We can't calculate the slope, and we can't calculate the area. Well, let's see what we can do. Let's say if instead of plotting speed versus position, we plotted speed versus the square root of position, which we see is actually part of the equation, right? If I sort of separate this out, there's the square root of 2a times the square root of delta x. Well, when I do that, this forces the equation to look like y equals mx plus b, where now we're going to plot speed on the y, delta x on the x, and that means that whatever is left behind is representing the slope of this line, just having to be no y-intercept. And so it turns out plotting speed versus square root of x sort of magically straightens the curves. In fact, this process is known as straightening curves. And now, if we were to take the slope of this line, well, we can see from what we did here, mapping this equation to what looks like y equals mx plus b, the slope would represent the square root of 2a. Now, that's not exactly something useful, but then you could calculate the acceleration by squaring the slope and dividing by 2. In other words, this process takes a curved graph, straightens it out, and then you can calculate something useful from that graph. Now, there's all sorts of other options. If we go back to the original time-independent kinematics equation and again pretend that the initial speed is 0, what happens when we plot speed squared versus delta x? So that's what I see in this equation. I see speed squared, and I see delta x. I see those quantities. Well, now, if I sort of, again, assume initial speed is 0, now it looks like y equals mx plus b, where speed squared is going to be on the y, delta x is on the x. Now the slope is representing 2a. And so once again, this will straighten the curve. And so you've got all sorts of options. When you look at an equation that's obviously not a straight line, what you would do with it to straighten the curve. But my general advice is plot what you see. So in this version of the equation, I see speed, so I don't do anything with it, and I see x under the square root, so I take the square root of x. I plot what I see. In this version of the equation, I see speed squared, so I square the speed, but there's nothing happening with delta x, so I just leave it alone. And so you plot speed squared versus delta x, you're going to get a straight line. So in general, anytime you're looking at an equation that we know when you plot it will not form a straight line, and you want to straighten the curve, well, just plot what you see. Whatever is happening to the quantities in the equation, do that, and then if it helps you to write it, top bottom here with y equals mx plus b, and just see how everything lines up, that will let you know what is represented by the slope and possibly the y-intercept.